Hello everyone, and thank you for coming into this presentation. I hope you're happy and healthy wherever you are. My name is Ali Dehkordi and I'm with RTDS Technologies in Winnipeg, Canada. The title of this presentation is a MultiStar synchronous machine model for real-time digital simulation and its applications. The content of this presentation is introduction and motives for modeling polyphase machines, analysis of a MultiStar synchronous machine, develop models and simulation results, and at the end, conclusions. Now, what is a polyphase machine? A polyphase machine is a machine that has 3 or more phases on a stator or rotor. For example, in the picture here, we have a polyphase machine with symmetrical displacement. What are the types of polyphase machines? The one that we've shown here, symmetrical displacement. We previously have shown how to model them. A split phase or multi-stator. This is the type that we're going to talk today. And sometimes you have sets of 3 phase with no magnetic coupling, only electric coupling between them. What are the advantages of a polyphase synchronous machine? With the application of polyphase synchronous machine, we could reduce the electric torque pulsation. We'll have more reliability and redundancy. You could lose 1 or 2 phases and still operate the machine. You will have lower current rating per phase, and as a consequence, you have lower ratings for power electronic converters. You also have reduction in noise characteristics and copper losses. For those reasons, these machines have applications in naval applications, submarines, electric ships, new schemes of wind turbines, electric traction, and electric vehicles. Now, why do we want to model them in real time? Real-time digital simulation is a fully digital simulation where all calculations required to determine the transient state of power system and servicing of IOs are completed within a time interval equal to the simulation time step. In order to have hard real-time solution, simulation results must be in synchronism with the real-world clock. Such a response provides possibility of closed-loop testing of equipment. And because some of our customers recently inquired about having such machines in their applications, naval or renewable energy wind turbine applications, we decided to model such machines. We have previously modeled polyphase, symmetrical polyphase machines, and now we're looking into multi-star machines. In order to model a multi-star machine, the first step is analysis. Now, what are the goals of such analysis? Is first of all, we would like to understand machine and its winding arrangement, predict its behavior, equivalent circuit and parameters, and find a suitable method for simulation. Now, the first step for analysis is understanding the winding arrangement in a multi-star machine. Generally, a multi-star machine has L sets of windings with K phases for each winding. For example, this arrangement that you see here is to a star, and each star has 3 phases. Now, the angular displacement between each set is generally pi over n. N is the total number of phases. Here we have 6 phases. The angular displacement is pi over 6 or 180 over 6, 30 degrees between each set of phases. This kind of arrangement allows reduction, minimization of the torque pulsation. Now, the problem is that now we could have very diverse arrangement of windings. L could be anything, K could be anything, and we want to analyze this machine with single theory. To do that, first step is to transform it to a winding arrangement which is called fundamental winding configuration. For example, here, if I flip phases C1 and C2 180 degrees, flip them here and here, I get this arrangement. Now I have arrangement from 0 to 180 degrees with the phase shift of pi over n. You could do that for any multi-star machines. Even for polyphase symmetrical distribution, you can convert it with a transformation to 180 phase progression, or what is called fundamental winding configuration. Next step is analyzing a machine with 180 degree phase progression, or what we call fundamental winding distribution. Previously, we've shown and we know that a machine with 360 degree phase progression, a polyphase machine, symmetrical polyphase, you could analyze it with Fortescue symmetrical component transformation. We know that Fortescue's transformation diagonalizes the inductance matrix of such a machine. And from there you can go to alpha beta or DQ for a polyphase distribution, symmetric here over 2 pi. Here we have a 180 degree phase progression. Or what we call single pole symmetry. We need to have a new symmetrical component transformation which is designed for 180 degree phase progression. And based on that, we can analyze such a machine with 180 degree phase progression. You can work out the math, but and go to symmetrical component alpha beta or DQ. But as an example, here we have alpha beta component for 180 degree phase progression for such a machine. Here delta 1 is pi over n or pi over 6. First row is your alpha component, last row is your beta component, and then you have some additional rows that correspond to the harmonic components for third and fifth harmonic. One other math subject that we need to take care of and keep in mind is the leakage inductance matrix. Often we think that for a synchronous machine the inductance matrix is diagonal, but it's not. If you think about it, for the end windings, you have couplings between all windings, even for three-phase. If your phase progression is symmetrical, the format of your inductance matrix is what we call cyclic symmetric. The first row is shifted and becomes second row. When we have 180 degree phase progression, the type, the shape, the structure of the leakage inductance matrix becomes what we call tuplet structure. And this is shown here. So some of the elements that you start with, they start from the end with the negative value and they reach in the middle. One can show that symmetrical component transformation that previous page we have defined for 180 degree phase progression can diagonalize this matrix as well. Now based on that, we can extract the D and D axis and Q axis equivalent circuit for the machine with 180-degree phase progression. As you can see, there are additional zero sequence circuits based on the number of phases. Here we have 4 extra for alpha 3, beta 3, alpha 5 and beta 5 axes. If you have odd number of phases, you will have a homopolar zero sequence circuit. The zero sequence circuit that we are familiar with for 3-phase, for example. Now, you see here we have this voltage term for D and Q axis, but we don't have it for the alpha beta components here. And that is because we assumed ideal machine for our machine. We said that we don't have space harmonics included and the permeance is sinusoidally distributed. One can show that if you have space harmonics included, some of them, for example, for a 6-phase machine for 3 and 5, you could actually still diagonalize it and you have additional voltage sources here. That means that harmonics also contribute to production of useful torque. So now, based on the description that we have developed a MultiStar synchronous machine model for our real-time digital simulator. Here's the icon for the simulator for this machine. As a user, you could model up to 4 stars. Each star is 3-phase for this model. You could have access to one neutral, multiple neutrals based on the number of stars, or access to both ends of each winding if you want to put converter on both sides. The model is implemented in both main and substep. The table here shows the execution time in nanosecond for the number of phases. From 369 to 12, we could have 400 up to 1300 nanosecond for execution time. Here are the simulation results and validation. An offline model in phase domain, directly in phase domain, is developed. The simulation time is very small, less than 1 microsecond, and is compared against the proposed model. First test is a 6-phase fault on a 2-star machine. 2-star machine has 6 phases. Basically, all phases are connected together simultaneously. First graph is our field current. You see there is similar to a 3-phase machine field current when you have 3-phase fault, and both of these models are in agreement. Second graph is the stator phase A current. Next example is single phase fault on a 3-star machine, 9-phase. And again, you see the good agreement between offline solution and proposed model. Here we have an application example. This is a typical electric network for a marine vessel. Now, this is a bit simplified, but in principle that shows that operation. We have a 6-phase generator to a star with 2 diode rectifiers that provide voltage for DC bus. We have batteries and a hotel load, and then we have our propulsion system, which is PWM driving to a star PMSM with the converters. During the operation, what you could show that if you say stop supplying power to generators, the battery could take over and keep the vessel running through propulsion system. Here are some of the results with in a steady state for the generators. We have generator voltages and currents, and two-star arrangement can be clearly seen in the currents of the generators. Also, as expected, we have 12 harmonic component in the electric torque of this generator. That's the smallest harmonic that you get basically. Next example is on the motor drive side, propulsion system. As explained, the PMSMs are supplied through two three-phase converters. It's a two-star machine. Now, in a steady state, we stop the gating signals to the first leg of the converter, phase A. They're suddenly blocked. And you can see the variation of the voltages. One of the things that you could observe when you're on the simulation is that the machine, even though you lost the phase, lost the leg, you still maintain the voltages. You still maintain the speed. Here we have reached the end of our presentation. Based on we have analyzed the MultiStar machine based on what we call the generalized method for vector space decomposition. We defined a Fortescue symmetrical component transformation for 180-degree phase progression. Then we took it to alpha, beta, and DQ domain, and we solved the machine that DQ domain for that assumption. A detailed and flexible transient multi-star machine model is developed, applicable for both offline and real-time electromagnetic transient program. And we have shown a typical power system circuit for marine applications. That kind of implementation is similar to what we see in wind turbines, and so one could take that machine and some of the converters, controls, and model the wind turbine with such machines. At the end, I would like to thank you for watching this presentation, and I hope the best for you everywhere you are. Thank you. If you have any questions, please send me an email.